Law of conservation of momentum is one of the fundamental conservation law in physics. And now we'll start doing some questions where you can simply see that the correct application of law can solve complex questions pretty easily. Okay. The first question says two masses of 2 kg and 4 kg are held in place, compressing a spring between them, right? So let's draw a diagram showing what this question means, right? So we have two masses. One is of 2 kgs and another one is of 4 kgs, and they are held by a spring which is compressed. So this spring must have some uh, elastic potential energy, and they are held back by doing something, maybe by a string or something like that, right? So when they are released, the 2 kg mass moves away with a speed of 3 meters per second. Okay, so this 2 kg mass, this spring is released, basically starts to move with 3 meters per second. What was the energy stored in the spring? Okay, the question asks what was the energy in the spring, right? So because they're asking for the energy, it's very clear that we will need to apply law of conservation of energy, right, to get that energy. Now think about this, whatever the energy is stored in the spring is finally getting converted into the kinetic energy of two blocks, right? So that will be our starting point to think that how we can compute whatever the energy is required, right? Or whatever energy is there in the spring. So we can say the energy in the spring will be equal to my kinetic energy of 2 kg block. We can just call this A and B, right? Kinetic energy of block A plus kinetic energy of block B, because there is no friction or anything to take away the energy, so this energy remains conserved, right? Clearly the kinetic energy of A is given, so I'm going to write that down, half into mass 2 into 3 into 3, right? So that's 9. So this is the kinetic energy of A, which is going to be 9 joules. Now the kinetic energy of B, we can again write half into mass of the block B, which is 4, into velocity of B square, which we still don't know, right? So this is 2VB square. Now this is what we are looking for, right? This is what the question is asking. So we know this is now 9 2VB square. If we can somehow get the VB, basically the problem will be solved, right? So the way we can get the VB is now by applying law of conservation of momentum, right? So to see whether the momentum conservation is applicable or not, we can see that on this system, which consists of these two blocks and the spring, there are no other external forces acting on it, right? In the horizontal direction, right? So there is no net force acting on the spring in the horizontal direction on this system. Hence, my momentum will be remain conserved in the horizontal direction, right? So what is the initial momentum? Which means my momentum of the system initial will be equal to my momentum of the system, which is final. So what is the initial momentum? Both of them are stationary, right? So there is no speed. So my initial momentum of the system going to be m into 0 plus m into 0. So my initial momentum is going to be 0, right? Now we look at the momentum after the release, right? So after the release, if we take the left side to be negative, we can simply say the momentum of this block A is going to be 2 minus 3, which is towards the left, right? So this is going to be 2 into minus 3, and then plus whatever with the speed of this block, right? So 4 into VB, okay? And this will remain to the equal to the initial momentum, which means this will be equal to 0. So now we can see here, this is minus 6 plus 4 VB will be equal to 0. Hence my VB is going to be 6 will go on that side, divided by 4 is going to be 6 by 4 or 3 by 2 meter per second, right? So now we have this unknown which we are looking for. We are going to substitute it over here and we'll get our answer pretty easily, right? So 2 into VB square will be now 9 divided by 4, okay? This and this will cancel. Now we have 9 plus 9 by 2 is going to be 4.5, and our answer will be 13.5 joules, right? So we'll often see questions where you can apply the law of conservation of momentum pretty easily. Very simple algebraic equation. All we need to do is be careful with the signs, right, or the direction. Whatever sign convention we choose for the initial momentum, we will use the same sign convention for the final momentum to get our answer like that. Okay, the combination of energy as well as momentum makes very good questions and usually do come in the exam. So let's look another one very quickly in this video itself. So this is two masses M and M are held in a place compressed by a spring between them. So very similar situation like last question. Okay, same similar situation. When they are released, the M moves to the left. So now when the spring is cut, basically this M moves towards left with a velocity v. Okay, what is the change in momentum of capital M? Right, that is what the question is asking. Right, so now you can clearly see there are no other forces, external forces acting on this system from outside. Right, so there is no friction, nothing. The spring force which is acting on these blocks is an internal force. Right, so there is nothing, no force acting on the system from outside which can change the momentum. So my initial momentum of the system, right, will be equal to the final momentum of the system. Okay, and initial momentum will be zero because they both the masses are stationary in the beginning, right? And the final momentum will be this mv will come with a minus sign, right? And this will be my final momentum for the block M. Okay, so what will be the final momentum for the block M? This is going to be equal to mv will go on the other side, equal to mv. Okay, and what was the initial momentum of this block M? That was zero. So there is a change in momentum, final minus initial, which is going to be equal to small mv, right? And with that, the net change in the momentum will be equal to zero. So whatever momentum these blocks take away, the same momentum this blocks gets, but in the other direction. So that net the momentum is zero as per the initial momentum, right? And that is what the law of conservation of momentum helps us understand. And these are very good questions which usually comes in the exam. So now we'll start looking at some of the collision questions in the next video.